Breaking news: the United States government has shut down. In a move sending shockwaves through the scientific community, NASA has been forced to cease all public communications. Its website's going dark, its live feeds cut. This unprecedented information blackout coincides to the very hour with the closest approach of 3I Atlas, the third interstellar visitor in human history to the planet Mars. Our robotic eyes are there, waiting, but the line back to Earth has been deliberately severed. What is going on? As a veil of silence is dropped over one of the most anticipated astronomical events of the century, millions are asking the same questions. Why is the government suppressing this information? Why is NASA shutting down just in time? Now, entering the fray is Harvard astronomer Avi Loeb, who is publicly pressing the United Nations to get involved.
Then currently there is no international organization. Obviously, alien technology would be a threat to all humans on Earth. It wouldn't care how we split the land on this rock that we call our home, the Earth. And so it's an international matter, and we need to be organized in that fashion.
Citing a profound crisis of transparency, Loeb argues that the U.S. government and NASA are actively refusing to provide critical information regarding 3I Atlas. His plea to the international body reframes the situation from a simple budgetary squabble to a potential global security issue. If humanity is on the cusp of a monumental discovery, he insists, the data cannot be held hostage by the politics of a single nation. Loeb's alarm has ignited a firestorm. YouTube and other channels have erupted, a torrent of speculation pouring into the information vacuum left by NASA. Theories of metallic objects, alien probes, and covert military operations run rampant, fueled by a potent mix of public fury and anxiety. Millions watched in disbelief as NASA, the beacon of human exploration, seemingly just pulled its servers and vanished from the public sphere, citing a lack of funding. The official reason feels insultingly mundane against the cosmic backdrop of the event it conceals. The world is on edge, and the question echoes across the globe: what is going on?
The scientific stakes of this celestial encounter are immense. 3I Atlas is only the third object from beyond our solar system ever to be observed, a priceless messenger from another star. Following the perplexing Oumuamua, which defied easy classification, and the more conventional comet Borisov, 3I Atlas offered a critical third data point. Its close pass of Mars presented a golden opportunity for observation from a non-Earth perspective. I chanced to study its composition and behavior in detail. The European Space Agency, ESA, was broadcasting its plans, preparing its orbiters for this very moment. Yet, just as this historic window opened, NASA's assets, most notably the Mars Reconnaissance Orbiter with its HiRISE camera, a telescope powerful enough to spot a coffee table on the Martian surface, were effectively blinded to the public. The official explanation for the blackout is both simple and maddeningly bureaucratic. Legally, the shutdown was governed by the Anti-Deficiency Act, a policy that mandates the cessation of all non-essential government functions, including public outreach, during a funding lapse. It was, by the letter of the law, standard procedure. But perception is reality. In the glaring absence of any official updates, images, or data streams from the world's premier...
If it's technological, it would maneuver, or it would release some mini probes, and or it will broadcast some signal, or it will have some artificial lights coming off it, not just...
Unprecedented is happening. By the end of 2025, 7 major comets will sweep through the inner solar system in just 6 months. A cluster so dense, our best survey telescopes have never seen its like. Among them is a true outsider, 3I/ATLAS, the third interstellar object of its kind ever found. Its bizarre chemistry and enormous green atmosphere set it apart as a complete cosmic wildcard. The statistical odds of a convergence like this are staggeringly low, under 0.5% in any given decade. The question astronomers are asking is whether this is simple chance or a sign that the sky is not behaving as we expect. 7 visitors are approaching Earth. A headline that sounds impossible, but it's real. By late 2025, 7 sizable comets will converge on the inner solar system in just 6 months. An occurrence so rare that leading surveys like Pan-STARRS and ATLAS have never logged anything close. Nestled among them is 3I/ATLAS, only the 3rd interstellar comet ever detected. Its exotic chemistry and vast green coma make it the ultimate cosmic wildcard. The odds of this happening by chance, less than 0.5% per decade. Is it just astronomical coincidence, or are we seeing something that breaks the rules of our sky? The answers and the risks start here.
A silent global network. The reason we know about this impending spectacle is due to a global network of robotic telescopes, the world's automated comet hunters. Systems like Pan-STARRS in Hawaii and ATLAS in Chile and South Africa relentlessly scan nearly the entire sky every few nights. These are not the observatories of old, with astronomers peering through an eyepiece. These are data-gathering machines, digital sentinels, whose sole purpose is to map the changing heavens with inhuman precision. Finding a ghost. Their cameras are incredibly sensitive, capable of spotting objects as dim as magnitude 21, a level of faintness so extreme it's like trying to spot a single candle flame in London from a vantage point in New York. Their software doesn't look for objects, it looks for movement. Every image, a mosaic of millions of stars and distant galaxies, is compared against a digital memory of the cosmos. If a single pixel of light has drifted from one frame to the next, an alarm is triggered. This digital vigilance has completely changed the game of comet discovery. 20 years ago, finding a new comet meant months of patient sky watching and a healthy dose of luck. Now the number of finds has exploded. Faint, distant visitors that once slipped by unnoticed are now cataloged, tracked, and analyzed in real time. But for all this power, these systems were built to handle a steady trickle of discoveries. What's happening now is a flood. Before we dive deeper into this celestial traffic jam, it pays to have a quick cheat sheet. To grasp the true scale of this event, we need to understand the language astronomers use to describe it. First, there's perihelion. It sounds complex, but it's simply a comet's closest approach to the Sun. Think of it as the climax of the comet's journey. It's the point where the Sun's intense heat and radiation do their most dramatic work, turning a frozen, inert nucleus of ice and rock into a spectacular showpiece of gas and dust. For every comet, perihelion is when their real action happens, the moment it shines brightest and is most active. With 7 comets all reaching their perihelion in a narrow window, our solar system is set for 6 months of continuous overlapping climaxes. Next is the astronomical unit, or AU. Space is vast, and miles or kilometers quickly become meaninglessly large. So astronomers use a simpler yardstick, the distance from the Earth to the Sun. 1 AU is about 93 million miles, or 150 million kilometers. If you hear that a comet's perihelion is at 0.5 AU, it means it's diving into a point twice as close to the Sun as our own planet, subjecting it to 4 times the intensity of solar radiation. This simple unit makes it easy to visualize just how deep these visitors are venturing into the solar furnace. Then there's the magnitude scale, which measures brightness. The key trick to remember is that it works in reverse, like a golf score. Lower numbers are better, meaning brighter objects. A magnitude of 6 is the faintest star most people can see with the naked eye under perfectly dark skies. A star like Polaris, the North Star, sits at around magnitude 2. So when predictions suggest a comet might reach magnitude 2 or 3, it means we're talking about an object bright enough to be easily seen without a telescope, a prominent ghostly beacon in our dawn or dusk sky. Finally, there's the matter of tails. Every comet grows at least 1 as it nears the Sun, and often 2. They are not the same.
The dust tail is the most intuitive. It's a broad, pale, and often curved plume made of tiny dust grains shed from the nucleus and gently pushed away by the pressure of sunlight itself. It tends to be yellowish or white and follows the comet's orbital path like a luminous wake. But the second tail is far stranger. The ion tail is a thin, straight, and often electric blue blade of light. It's made of gas molecules in the coma that have been electrically charged by the sun's ultraviolet light. This charged gas, or plasma, is then grabbed by the solar wind, a constant stream of particles flowing from the sun, and hurled directly away from the sun at incredible speeds. This means the ion tail acts like a cosmic windsock, always pointing directly away from the sun, regardless of which way the comet is traveling. With these terms in mind, the true significance of the 2025 event becomes clearer. This isn't just a handful of faint smudges. It's a lineup of objects, some predicted to reach brilliant magnitudes, all making their closest approach to the sun in quick succession, promising spectacular displays of both dust and ion tails. Statisticians who work with comet survey data sometimes joke that the universe is stingy with its surprises. In a typical 6-month stretch, the odds say we should expect 2, maybe 3 comets bright enough for a backyard telescope. The rest are faint, distant, and destined for the archives. But late 2025 throws those expectations out the window. 7 significant comets, each with a perihelion packed in a single half year, have set off alarm bells in every Monte Carlo simulation run by comet population modelers. The numbers are stark. Even with our vastly improved technology, simulations show that a cluster of 7 in one season is a profound statistical outlier. The chance of it happening is less than 0.5%. Some models, factoring in the predicted brightness, spit out odds closer to 1 in 1,000 years. The rarity isn't just a product of better cameras. Survey efficiency can find more faint wanderers, but it doesn't conjure up a septet of major visitors out of thin air. The 2025 lineup stands apart from anything logged in the digital era, and even the old photographic records struggle to find a parallel. For data scientists, this is the kind of anomaly that demands a second look. Are we seeing the aftershock of a distant collision that sent a wave of objects hurtling our way? A strange fluke of gravitational dynamics in the Oort cloud, the vast, mysterious reservoir of comets far beyond Pluto? Or is it just a cosmic coincidence so rare it almost feels scripted?
This unprecedented event is creating a very real drama back on Earth. The digital systems that hunt for these comets are now flagging more candidates than anyone thought possible, pushing the limits of what they were designed for. Engineers and operators, usually content to let the algorithms run, are now glued to their monitors, watching as the data pipeline lights up. For the first time, the machines are struggling to keep up with the sky. Coordinating follow-up observations between the world's major telescopes has become a logistical nightmare. With so many targets appearing at once, there simply isn't enough telescope time to go around. Astronomers are being forced to make tough choices. Which comet do you study? The bright one that promises spectacular pictures, or the faint, interstellar one that promises revolutionary new science? This 6-month squeeze is turning the sky into a living laboratory, but it's a laboratory where the experiments are all happening at once. With the scientific world scrambling to keep up, the fundamental question remains, who exactly are these 7 visitors? From the faint and distant to the bright and spectacular, each one carries its own story, its own set of clues to the history of our solar system, in one case to the history of a solar system far beyond our own.